Hello?
Sir, you are audible, sir.
Okay. Huh? Okay. Okay. Hello?
Sir, audible, sir.
Okay. So let us start. Sorry for the disturbance.
Okay, sir.
So Hakel molecular orbital. Okay. So you have to put beta if there is a carbon bar, otherwise 0, and diagonal elements are alpha. So alpha is 0 and beta is 1, then it becomes the simply adjacency matrix. So energy levels Ej of the pi electrons are related to the eigenvalues. Okay, when they jumps the electrons from one orbit to other orbit, they generate some energy. Okay, and that is epsilon j related by this ray alpha plus beta into lambda j. So in the HMA approximation, the total pi electron energy is nothing but sum of the Gi into epsilon I. Okay, where Gi is the occupation number. So if you replace this epsilon I with alpha plus beta lambda j, you will get here total pi electron is n alpha plus beta into summation of Gi into lambda. So in most of the cases, Gi is 2, otherwise 0. Okay, so it becomes 2 if lambda is positive, otherwise 0. Okay, if lambda is less than 0, it is 0. Okay, so you'll get here n alpha plus 2 times beta into sum of lambda only for positive, because for other it is Gi is 0, so we are not considering the negative eigenvalues, and if it's 0 eigenvalue also they are neglected, so only positive eigenvalues. And we know that the sum of the eigenvalue is 0, and the sum of the positive eigenvalues is same as the sum of the negative eigenvalues with different signs. So instead of writing 2 times summation of positive eigenvalue, this can be written in the form of summation of mod of lambda, where all lambda is taken here, positive as well as the negative, because it is 2 is there. Okay, so it is n alpha plus beta into sum of lambda. Now see, observe here, n is fixed, alpha and beta they are the constant fixed. So what is left? Only this part, summation of mod of lambda. So as I'm so method is they are interested only in this part. Okay, they are not bothering about n alpha and beta because it's a fixed only. Okay, so this part is called the graph energy. So Gutmann has denoted this quantity as epsilon j and called it as a graph energy. So it is nothing but sum of mod of lambda I, where I is 1 to n. Okay, so there's a direct relation between the total pi electron energy and the sum of the absolute values of the eigenvalues. So this is a relation given by the Coulson in the form of integration for the graph energy. Okay, it is 1 by pi integration of minus into plus n minus I lambda pi dash gi lambda divided by pi g, where this bold I is nothing but square root of minus 1. Okay, and pi dash is the first derivative of the characteristic polynomial. Okay, so same can be expressed in this form. Okay, so energy can be expressed in the form of the integration. Okay, so just I will outline the proof of this result. Okay, so if suppose lambda 1, lambda 2, lambda n are the eigenvalues or roots of the equation, okay, then the characteristic polynomial in the form of z can be written in this form, product of the factors z minus lambda j. You differentiate this with respect to z and divide by pi of jz, you will get the summation of 1 divided by z minus lambda. Just differentiate and the divide it. Okay, you will get this. So from here, we can write this is there, so multiply both sides by z. You get this summation of z divided by lambda minus lambda z. This can be expressed in the form of 1 plus lambda z divided by z minus lambda z. Then separate it. So summation of 1 n times, you get n plus summation of this quantity. Okay, summation of this quantity. Okay, so taking n on the other side, we'll get this. So as the mod z tends to infinity, okay, this quantity tends to 0. Okay. So we know that Z pi dash GZ divided by pi GZ is this one. Okay. Now consider this contour. Okay. Where these are the positive eigenvalues and these are the negative eigenvalues. Okay. So we are taking the positively oriented contour in this anticlockwise direction. Okay. So as per the Cauchy's formula, we know that 1 by 2 pi integration of dz divided by z minus z naught is 1 because here f of z is 1. Okay. So f of z naught means 1. If z naught is the interior point and it is 0 if the on the exterior of the contour. So therefore, from here, okay, integrating this part over the contour, okay, you will get as per using this Cauchy's formula 1 by 2 pi integration of lambda z, sorry, it's equal to this one, summation of lambda z divided by z minus lambda z. So you'll get this one. Okay. So using the Cauchy's formula, we'll get this summation of lambda z over the positive eigenvalues. Okay, over the positive eigenvalues, and that is nothing but energy of G divided by 2. Okay. So energy of G is equal to 2 times this. So in the limiting case, when it becomes infinitely large, the only non-vanishing contribution to that integration is through the y-axis. Okay, along this curve it is vanishing when it is arbitrarily large. Okay, so it is only along the y-axis. So energy of G can be written in this form. Okay, from here by cross multiplying you can get energy of G equal to 2 times this. Okay, so you get this one. That is split into 2 parts, minus into infinity along the curve, and then infinity to minus infinity along the y-axis. Okay, so this part is vanishing as mod z tends to infinity. Okay, so only left this part. So and this is along the y-axis. So along the y-axis, x is 0, so z becomes iy. Okay, z becomes iy. So simplifying this, we can get the energy of G in the form of this integration, where I is nothing but square root of minus 1. Okay, then this is a bound for the energy. Okay, so energy of G is always greater than square root of 2m into n into n minus 1 into determinant of A to the power 2 by n. Taking the determinant is taken as absolute value. So again, energy of G square. Okay, because energy of G is sum of the mod of lambda square. So square it, you will get a sum of lambda square plus sum of lambda into lambda j. Okay, so for this quantity, because this is 2m, so for this quantity, so geometric mean of positive numbers is always not greater than their arithmetic mean. So using this relation, the geometric mean is this arithmetic mean is greater than or equal to geometric mean. Okay, so product of lambda into lambda j is simplifying, we'll get lambda raised to 2 to the power n, that is 7. And product of lambda is nothing but the determinant value. Okay, it is nothing but determinant value to the power 2 by n. So this can be replaced with the n into n minus 1 into determinant of a to the power 2 by n here. And this is 2m. So you can get the energy of G is greater than or equal to square root of 2m into n minus 1 into determinant of a to the power 2 by n. Okay, so this is the lower bound. Same way, we can get the upper bound as a square root of 2mn. And this is by Cauchy's square inequality. We can write sum of lambda square is less than n into sum of lambda square. And this sum of mod of lambda is energy of G, and this is 2m. So simplifying this, we'll get the energy of G is less than square root of 2m. So energy of G is always lies between this quantity. Okay, this is a lower bound and this is upper bound. Okay, so these are some other results. Energy of G lies between 2 times square root of m and 2m. And this is recently means 2001, Coulomb and Moulton given the best possible bond for the energy of graph, but the condition is that 2m is more than or equal to n. Okay, so energy of G is less than or equal to this quantity. This is what we have proposed, so and myself in the 2008 in terms of the this one nm and m, okay, where m is the Zagreb index. So energy of G is less than 2 into square root of m by n1 plus 2 times square root of n1 minus 1 into m minus m by n1. Okay, equality holds for this graph. Okay, so there are several bounds available for the energy of a graphs. Okay, now for a molecular graph is a graph having the degrees either 3 or 4 or less than 4. Okay, not all graphs. Okay, so in the most of molecules they are the maximum degree 4. So in such graphs, the Maclaurin shows the energy is always equal to A into square root of 2m, where A is approximately 0.9. So here for n fixed, m is varying. Okay, so in the complete graph, the number of lines are more. So one thought that for complete graph, the energy is more. Okay, because m is varying, and the complete graph, the m is maximum. That is n into n minus 1. So in this observation, Gutmann conjectured that among all graphs with n points, the complete graph has the maximum energy. So energy of any graph is always less than equal to energy of a complete graph. Okay, it is not E of A, it is epsilon of Kn, 2 into n minus 1. But that is not the case. Okay, they observe because it is a molecular graph, but in general, it is not possible. Consider this graph. Okay, icosahedron. Okay, on 12 points. So its spectra is this given in this bracket, and if you calculate, the energy is 23.4166, and the energy of the corresponding complete graph is 22. So energy of this graph is more than the energy of complete graph K12. So this conjecture is not holding. Okay, it is not true. Okay, so for some graphs it is old, but not in general. So we propose the method to construct the graphs for which this conjecture is not true. Okay, so spectra of Kn is this. The spectra of its line graph is given by this. So from this, we can get the energy of L of Kn as 2n square minus 6n. And the energy of the corresponding complete graph is n square minus n minus 2. Okay, so for n greater than or equal to 5, this quantity 2n square minus 6n is always greater than n square minus n minus 2. So for different value of n starting from 5, one can get the graphs, complete graphs, okay, whose line graphs disprove the conjecture of the Gutmann. Okay, so there are many graphs can be constructed, okay, for which the conjecture is not true. So from that, the problem comes that if complete graph has no maximum, then which graphs has the maximum energy? So that is a main problem now to get. So many people are trying it, and so far few are succeeded with certain conditions. But in general, so far we don't know among all n vertex graph which graph has the maximum energy. Okay, so Hammers and Jiang, they showed that there is a graph with maximum energy with n is 4 k raised to 4, but for not all n. So this is a problem I quoted here of finding the graph with n vertices having maximal energy is still open. Okay, so it comes the hyperenergetic graphs. Okay, so graph is called hyperenergetic if the energy of G is more than the energy of the complete graph, because complete graph has not the maximum energy. So there are graphs. So we call because complete graph has the maximum number of lines, no? So we put that as a middle one. Okay, so which graph has the more energy? Then complete graph is called the hyperenergetic graphs, and the graphs which are having the energy less than complete graph are called non-hypergenetic. Okay, so here for m is greater than 2n, the line graph is hypergenetic. Okay, I'll skip the proof. If m is less than or equal to 2n minus 2, then G is non-hypergenetic. Okay, these are some conditions. Okay, but these are only sufficient, not necessary. Now consider this type of graphs. Okay, G1 is a graph with n1 points m1 lines with this condition, m1 is less than 2n minus 2, and another G2 is graph. So if we take this union graph, then it is a non-hypergenetic. If we take one point is coincident, then also it is non-hypergenetic. If we join G1 and G2 with line, then also it is non-hypergenetic. If we join G1 and G2 with two lines, then also it is non-hypergenetic. If we join G1, this is of course G1, not G2. It is G1 with G2 like this. Then this is also not hypergenetic. Then last one about the equigenetic graphs. So graphs having equal energy. Okay. So just like a co-spectral graphs. Okay, there are different graphs having same spectra. Like that here also different graphs having same energy. Okay. So such graphs are called equigenetic graphs. For example, if we consider this triangle, this C4 and these two categories. So this triangle has the eigenvalue is 2, minus 1, minus 1. This cycle C4 has the eigenvalue 2, 0, 0, minus 2. And these two lines together has the eigenvalues 1, 1, minus 1, minus 1. And each is giving the energy 4. Okay. So one is triangle, one is a cycle C4, and one is a 2K2. Okay. So they are different graphs but having the same energy. Okay. But these two are not having the same number of points, whereas these two are, one is connected, one is disconnected. So here is the with same number of points. Okay. This is a cycle C5, and this is another one, tetragonal pyramid. Okay, this graph GD. Okay, its eigenvalue is given in this form. Okay, 2 root 5 plus 1 by 2 and so on. And the eigenvalues, these graphs are root 5 plus 1, 0, 0, minus 2, minus root 5 plus 1. Okay, and if we calculate the energy of means, if we take the sum of the absolute values of these values, it is 2 plus 2 root 5. Okay, so see, they are having the different eigenvalues. Okay, means they are not all cospectral, but even though the energy is same. These are another two graphs having the different spectra, but energy is 16. Okay, so this is a line graph, equivalent line graphs. If lambda 1, lambda 2 are the eigenvalues of G, then the eigenvalues of its line graph are lambda plus r minus 2, and the remaining are minus 2. Okay, so again take its line graph, that is the second line graph. So you get the eigenvalues as lambda plus 3r minus 6, 2r minus 6, and minus 2, these many times. Okay. Then for r greater than or equal to 3, this lambda plus 3r minus 6 is positive. Similar to r minus 6 also positive. Okay, for r greater than or equal to 3, and lambda lies between minus r to r. So if we take the sum of the absolute values of these eigenvalues, we get the energy of second line graph as 2nr into r minus 2. So irrespective of structure, okay, you take any line graph, okay, with regularity more than or equal to 3. If we take its second line graph, the energy is remaining same. That is depending only on the number of points and the number of degree. Number of points and the degree of a graph. Structure may be anything. Okay, it is not depending on the structure. It is depending only on the r and n. Okay, so if you take the second line graph of all regular graphs where regularity is more than or equal to 3, the energy is given in them. So all such second line graphs has the same energy, but spectra is different. Okay, they are having the different energy. Okay, so in general, we are instead of second line graph, we are taken it is for the k plus 1th line graph. Okay, then this is a graph product. Tensor product of two graphs G and H is the graph G cross H, whose vertex set is V of G cross V of H, and two vertices U, V, X, Y are adjacent in G cross H if U is adjacent to X in G and V is adjacent to Y in H. Okay, so these two graphs and its tensor product is this. So from this, you can see, if suppose lambda 1, lambda 2, lambda n1 are the eigenvalues of G1, and the mu1, mu2, mu n2 are the eigenvalues of another graph G2, then the eigenvalues of their tensor product is lambda into mu j. So from this, the Bioquestioner in 2004 obtained the energy of the tensor product as this one. So energy of the tensor product of G1 and G2 is energy of G1 into energy of G2. Okay, so if we consider energy of K2 cross G and the energy of C4 cross G, it is 4 times energy of G. Okay, so these two graphs are different. Okay, and since K2 and C4 they are having different spectra, so they are also not cospectral, but energy is same. It is 4 times energy of G. So thus, Bioquestioner has constructed pair of equivalent graphs for all n greater than equal to n congruent 0 mod 4. Okay. So similarly, Stefanik has constructed with similar method for n congruent 0 mod 5. Okay, he has constructed a pair of graphs for all n where n is congruent to 0 mod 5, considering these two graphs. Okay, then we constructed for all n. Okay, so for that we are taken join. Okay, so join of two graphs is nothing but the taking the joining all points of this graph to all points of second graph. That is called the join of two graphs. Okay, so characteristic one of the join of two graphs where G1 and G2 are regular is given in this expression. So from this, the energy of join of two graphs is energy of G1 plus energy of G2 plus square root of R1 plus R2 squared plus 4 into N1 N2 minus R1 N2 minus R1 plus R2. Okay, so from this, we constructed the pair of graphs which are not cospectral, okay, but having the same energy for given n starting from 9. So for that, we have considered these two graphs, okay, G1 and G2. Okay, they are not a cospectral. See, from looking to the polynomial, we can observe they are not having the same eigenvalues. Okay, not the same set of eigenvalues, but energy is same. That is 16. Then consider any other graph H with P points and regularity R. Then join it. G1 join with H and G2 join with H. Then their energy is 12 plus energy of H minus R plus this quantity. So from here we can observe, okay, the G1 join H and G2 join H are equinergetic. Okay, and they are not a cospectral. Okay, and they are having the order as 9 plus p. Okay, because originally 9 points are there here in this graph. Plus you are joining one graph with p points. So total number of points will be 9 plus p. P starts from 0 to n. So one can construct it in this method the pair of graphs which are equianergetic but not a cospectral. Okay, for given. Okay, so this is the theorem that only explain. Then this energy of G with energy of G bar. So currently we are working along with my group of students that graph and its complement having the same energy, whether it is there, and it is there. Okay, so for example, the smallest one is C4. Okay, cycle C4 has the eigenvalue is 2, 0, 0, minus 2, and its complement has the eigenvalue is 1, 1, minus 1, minus 1. Okay, and their energy is same, 4. Okay. So we have proved that following graph satisfies that property. That is for n greater if G is a union of Kn. Okay, then the energy of G is same as the energy of its complement. And if we take the complete bipartite graph, then energy of its line graph and its complement has the same energy. Okay. Then recently, Ali alumni Mansoor and Rustoni, okay, it's a recent paper in 2020, determined all graphs satisfying energy of J with energy of G bar with at most 10 vertices. Okay, so up to 10 vertices, they have find out which pairs have the which graphs are satisfying this property. Further, they obtain up to the 10 points whose line graphs also satisfy this condition. That is energy of L of G equal to energy of L of G bar. Okay, and recently this we have done. Strongly regular with parameters n or lambda mu is an R-regular graph on n points in which any two adjacent vertices have exactly lambda common neighbors and two non-adjacent vertices have exactly mu common neighbors. So such graphs are called strongly regular graph. For example, Peterson graph, okay, or cycle C5. They are the strongly regular graph. So we have put here condition, means characterize a strongly regular graph with parameters n or lambda mu satisfies this condition. Energy of G is same as the energy of its complement. If and only if n minus 2r minus 1 is delta by t, where this delta is given in this form, that is 2r plus n minus 1 into lambda minus 1, and t is square root of lambda minus mu square minus plus 4 into r minus mu. Okay, so like that one can characterize class of graphs satisfying these properties. This is one of the class strongly regular graphs satisfying these conditions. Okay, or having energy of G equal to energy of G bar. Okay, and little bit at the end the equianergetic trees. So these are the two trees. They are not cospectral, but energy is same. This is another pair, T3 and T4 having the same energy. This is another pair. So there are several pairs are there having the same energy, but different spectra. Okay, but there is no such method to construct a equianergetic tree. So far, it is not done. Okay, only some species are there where you can check it. Okay, but in general, there is no method, there is no technique to test whether given trees are equianergetic or construct the equianergetic trees. Okay, so a little bit some other people also working on the equianergetic graphs. For example, Zubov, they report a method of obtaining infinitely many pairs of bipartite equianergetic graphs. Gani Pirzada and Imani constructed equianergetic graphs taking double graphs. Adiga Galaxy, they have constructed, they have given another method to construct the equianergetic graphs for all n greater equal to L. Okay. So there are a lot of scope is there to work on all these indices as well as the energy. Okay. Many problems are there, many, especially for this tree. Not much work is done on the equianergetic trees. So one can see here. Okay, so these are some references. Thank you. Thank you, ma'am. If any queries or something.
Hello.
Hello.
Hello. I am Dr. Lawrence.
Okay.
Sir, kindly suggest a new index
new index.
Indices, new indices.
New index means recently the people are working on this neighborhood indices and all that. Okay.
Neighborhood index. Okay, sir.
Neighborhood index, then degree distance indices,
Degree
okay.
distance. Okay.
Then inverse degree indices.
Okay, sir. Okay, sir. So, what any book for references for indices?
For indices, recent book is there. Just a minute.
Name the book, sir. Hello.
Hello. 1 minute. 1 minute.
Okay, sir. Okay.
Here a recent book is there. Handbook of Research on
Handbook of
Advanced Application.
Advanced
Hello,
application.
audible?
Audible, yes, sir. Advanced application.
Advanced applications of graph theory in modern society.
Graph theory in modern
society. Modern society.
Modern society. Thank you, sir. Thank you.
It is published by
Yes, sir.
IGI Global.
Okay, sir. Yes, sir. It's a nice presentation. Thank
Okay.
you. Thank you, sir. Thank you, sir.
Any other?
Hello, sir.
Hello, ma'am.
Your presentation are very nice, sir. Without lost a lot of energy, you continue the process along 2 hours. It's very great.
Okay.
Very great, sir. Like molecular graphs, hyper energetic graphs, equi energetic graph is unknown thing. So it was very great.
Okay.
Your students are very lucky, sir. Thank you, sir. Hands up to you, sir.
Thank you very much.
Sheila ma'am.
Yes, ma'am. Yes, ma'am. Feedback. Yes.
Over ma'am.
Now, it's a time for vote of thanks. It will be delivered by our department faculty, B. Rajalakshmi.
A very good afternoon to one and all. Thankfulness is the beginning of gratitude. Gratitude is the completion of thankfulness. Let me first of all start by giving glory to the Almighty God for bestowing His blessing and making this event a resounding success. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. A responsible man is a successful man. Yes, today's chief guest is such a man who disposes responsibility in a well-planned manner. I want to extend my heartiest thanks to Dr.H.S. Ramane, Professor, Department of Mathematics, Karnataka University, Dharwad, India. I am sure that the participants must have benefited by attending your session, sir. Thank you, sir. And I also thank the heart which always beats for us, who is none other than our beloved secretary, Dr. Sister Mariammal. Thank you, sister. The quality of a leader is reflected in the standards they set for themselves. A warm thanks to the leader with a high standard of goals who motivates to help us, who is none other than our beloved principal, Dr. Sister Catalina. Thank you, sister. Thankfulness may consist merely of words. Gratitude is shown in acts. I would like to express my most sincere gratitude to all the participants to attending this FDP. Without your presence, this event would not be a grand success. We expect your continuous support now and then. Thank you all the participants. Last but not least, it's my duty to deliver my words of thanks to our most responsible head of the department, staff members, all of our well-wishers, and special thanks to IDMC coordinator for their massive support to make this event to make this three days FDP a grand success. Once again, I thank you all.
Thank you, sir.
Thank you. Thank
Thank
you,
you,
Thank
ma'am.
you, sir.
Thank you very much. Thank you.
Thank you,
Thank you, ma'am.
And Helen, ma'am, you've done a very good job, ma'am. Keep rocking.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you. Thank
Thank
you.
you, sir.
Thank you. Today's session is over. Tomorrow, 10 o'clock will be short. Thank you. Today's session is